Hello, dear students. Today it is the lecture number 7th on tensors. So, in previous topic, you might have watched that video. How we talk about this vector transformation? If we go from some unrotated to rotated, from some xy unprimed to some primed system, right? As I already told you, so if we go from, so if we have this or that unprimed and this is our vector, and you rotate this. So suppose this makes some angle alpha with this xy, this coordinates, right? And you rotate this coordinate system through some angle theta. So we have this x prime and this is y prime, and, and this over r is makes some angle theta, right? So you have seen that. So when we talk about these Newton's law, we have that F equal to ma. So if we talk about the components, so component in this set, so that will be x here and nu, so it will be some x prime, right? So that means these components will not be equal. So components will be different. If you transform it, if you rotate it through some angle theta, right? Because you are moving in xy plane. So your ax prime will not be equal to x, but total that vector and the direction of that vector remains invariant. That remains the same. So, or we can say that here this f prime will not be equal to f, right? But the form of this equation, f equal to ma. So the form of this equation that fk mak, so this remains covariant. So this is covariant in both the planes. So we can have the same kind of relation in both the frames of reference because component wise they can be different. So यहाँ पे ax का value कुछ होगा, and when you rotate it through some angle theta, so the ax prime can be different, right? But overall this relation will hold in both the frames. So we are saying that this fk equal to mak, so this is covariant in both the frames of references, right? So this is what we have discussed in previous lecture. So before starting our lecture, so I'll add one more point here. Being a student of physics or a physicist, he has to have some, he has to gain expertise in various several theories of relativities. So he has to gain expertise in several theories of relativities. In addition to that, including that, if we changing from one coordinate system to another coordinate system. So if we go from some rectangular coordinates to some cylindrical coordinates, or from cylindrical to spherical polar coordinates, so he should be able to understand. You should get expertise how we can transform, how to do different vectors, or how do different physics laws transform if you go from some one frame to another frame. And similarly, one more point is that rotation and translation of coordinate axes. So that means if we like in this vector transformation, when rotating it through some angle theta, right? So how do these vectors transform? So that is basically that rotation or translation. So that means you are shifting your coordinates. So you are going from some x to x plus delta of x, right? So see the behavior, or see the form of the equation at some point x equal to x plus delta x, right? And if we change from some inertial frame to some accelerated frame, right? And there are some other transformation also. So one of the transformation that's called a conformal mapping, and we can have those space inversion also if we go from x to minus x, or we can have the time reversal also. So those transformation also in this time reversal transformation, we are going from t to minus t, right? Or space inversion when you go from x to minus x, or you talk about this conformal mapping also. So these are some other kinds of transformation that you can find in the course of these tensors, right? On the course that we are going to discuss here. So before discussing, let us talk about this because we have already discussed this translation and the this rotation and the translation of the coordinate axis, right? So I can right now. So if we talk about this system, so this one, this rotation and so this kind of this motion, you can say that when you are going from rotation, or you can say the boost and translation of the coordinate axis, so this includes our that Newtonian relative. So that means when you are talking about the relative motion or boost between two inertial frames. So this is basically when you talk about the boost or relative motion. Right? तो अगर हम देखेंगे relative motion or boost between the two inertial frames, so that is so you can say that that includes this Newtonian relativity. So Newtonian relativity is based on the absolute value of that time and space, right? So this is based on that absolute time and absolute space. So in addition to that, so these are the basic laws, so the basic foundation. So it is based on the absolute time and the absolute space. And what are the forms of the equation? What kind of equations are involved in this Newtonian relativity? So we have those well-known these transformations. Those are called Galen transformations. So we can have these that x prime equal to that x minus bt, y prime equal to y, and z prime equal to z, and t prime equal to. So these are these Galen transformations. And in addition to that, if we talk about the boost between the two inertial frames, so that is related to, we can say that that is subject to special relativity. So we have special relativity also. So we can add. So if you talk about now boost, so that includes, that's called a special relativity, right? So that includes that special relativity. You can take one example, and it is based on the foundation that the value of c. So it is based on the foundation that c is invariant. तो जो हमारा c है velocity of light, it remains invariant between the two frames of length, between the two inertial frames of length. So this is the basic foundation. Like in Newtonian relativity, we have that absolute space and absolute time, but here the velocity of c, the value of c remains invariant between the two frames, between the two inertial frames. And what kinds of equations are involved in this kind of this theory in special relativity? So we can have those transformation equations known as Lorentz transformation equations. So because we have those Lorentz transformations, that is x prime equal to, right? So this is basically that special that relativity. So that the basic equations that are involved in this kind of theory, that is those are Lorentz transformations, and we have this gamma, that's Lorentz factor. So this is clear to you. So in our other class you might have discussed these things, and or you can say that, so this is our beta, that's v by c. So we'll come across these maybe in coming lectures. So these are basically these Lorentz transformation equations that are involved in this kind of this when we talk about the boost between the two inertial frames of reference, right? Now, if you talk about now, if you go from this now, if you make now, if you talk, in one of our lecture we have discussed that how we can define these scalars, right? So we can say that in this kind of a thing. So if we talk about now this any theory of relativity, if you talk about this any theory of relativity, either it is that this Newtonian relativity, or you talk about the special relativity. So any theory of relativity is based on the foundation that what stays or what remains invariant when you make transformation, when you go from one inertial frame to another inertial. So that means any theory of relativity is founded on the scalars. That is based on the foundation of scalars. Because scalars remains invariant if you go from some inertia from one frame to some another frame of reference, right? So like scalars in one of our lectures. So in maybe that was lecture number first. So we have defined that how we can define a scalar when we go transformation from one coordinate system to another coordinate system, right? So we are saying that if some quantity remains invariant from one frame to another frame, that quantity is supposed to be that's called a scalar, or that's invariant quantity, right? And this definition of scalar somewhat matches with the tensors, because tensors transform the same way as do the scalars transform, right? Now, so that means now if you go from now, if we right now, if we are going from change of this, if we go from that coordinates, if we change the coordinates from some unprimed to some primate system, right? So if I write now, where I'm going now, change of coordinates from. So you are going from some unprimed to some primate system, right? So how you can define that? If you write now dx prime I, so that is equal to. So you can write this as. So can I write it this way? Because so this side this will cancel, so you get the same. So this is summation of j. So I will tell you, because j can run from, if you go from 1 to 3, 1 to 3. So like we have those x1 equal to x, x2 equal to y, and x equal to. Okay, so it includes all those coordinates, right? Because I'm going from some unprimed to some primed, so from some unprimed to some primed system, right? So if I talk about now, so if you write now the reverse of this transformation, so from some mm, primed to unprimed, so we can write this as, so what's our dfj then? So this is our if you write now, so this is for reverse transformation, for reversal transformation. So dxj will be equal to, so you write some another prime, that is summation over n, right? And you can write this as, this will be partial x prime I x j, because it's j, and partial x prime n dx. Okay. So this is when you are going from some prime to unprime, and this is the reversal transformation of this. Okay. Now use this dfj here. So use this dfj in this equation. So we can write that our dx prime I. So before that, okay, so that's clear. You can write dx prime this way, right? Okay, so you can write this as so this is equal to dxi partial x j by partial x prime, right? So यहाँ पे मैंने क्या किया? So instead of that dx j, I use this one. So that's partial x j by partial x prime I and dx prime n. Okay. So if I rewrite this term, so this term is equal to, so you are writing, तो if अगर मैं यहाँ पे use करूँगा, if I write here, because if I write here that this if I write now, so let me rewrite this as, so this is dx prime I equal to dx prime n, or you can write this as, so dx prime I summation over n, so that's equal to mm, partial x prime. Okay, and dx prime. Okay, so that means ये किसके बराबर होगा? So this dx prime I will be equal to dx prime n. तो ये इसके बराबर होगा. So dx prime I will be equal to dx prime n, right? So with some, if I use here delta in, so that means अगर मैं यहाँ पे ये use करूँगा delta in, so it is that chronicle delta, so it will be equal to 1. Okay, तो अगर I n के बराबर होगा, so this is dx prime. So that means this is equal to delta in. So you can write here, sorry, this is because we need to omit that n. So this is generally j. So that's, so that means this delta in is equal to this one. So this is our chronicle delta, right? तो अगर I n के बराबर होगा, so what will be the form? तो इसकी form क्या बनेगी? So that means अगर मैं I n के बराबर होगा, if I equal to n, so in this equation, so this will be equal to summation over. So limit that because I equal to n here, so this will be that partial summation over j partial x prime I by partial x j. So this clear because यहाँ पे I n के बराबर होगा, so this and this will cancel, this and this cancel, so this is equal to 1. So this is what I wrote, so that means this is our that transformation matrix, right? So this is our transformation matrix, and which is nothing, that's our chronicle data, right? So so as I already told you, because if you talk about now, as I already told you in tensors, so if you talk about now, मैंने आपको already बताया कि जो tensors होते हैं, they transform as the coordinates do. So that means tensors, it hardly matters which coordinate system you are using, right? Suppose, so I'm saying now tensors, you can write that tensors. Okay, so transfer these tensors transform as the coordinates transform, as the coordinates do, right? So it is independent of the choice of the coordinates, right? So it is independent of uh, so it is independent on the choice of the coordinate system, right? Suppose I will give you here one example. For example, if you take now, for example, if you write that f equal to that ma, right? Or this is equal to so this will be equal to that Okay, or you can write this as, so this will be fi equal to, no, you can write here, better is to write in terms of this x, right? Because I will take values at 1 and this x equal to 0. So that means it includes all those components, means ax, ay, and az, right? तो मैंने आपको ऑलरेडी बताया कि जो ट्रांसफॉर्म these tensors transform as do these vectors do, right? So that means it is independent of the choice of the coordinates. Let us take a simple example that if our that this f equal to ma, right? So I can write this as fi will be equal to this one, right? Or you can write this as fi equal to ma. Okay. Now if you multiply this term, this equation by, if you multiply this equation by partial x prime j divided by partial xi. Okay. तो मैंने यहाँ पे क्या किया? I simply multiply this term on both sides. That's partial x prime I by partial x prime j divided by partial xi, and this same term on both sides, right? Okay. So if I write here, so this term, so if you check this partial x prime j by partial xi, so this will be equal to 1. So when it will be equal to 1? If our j prime will be equal to I. So that means if j prime will be equal to I, right? So that means अगर मैं इस term में j prime किसके बराबर होगा? J prime should be equal to I. So in that case, this term will be equal to 1, right? And so what is the form of this? तो ये term क्या बनेगी? तो अगर मैं यहाँ पे j prime I के बराबर लूँगा, so this term will be equal to 1, and instead of that j prime I के बदले मुझे j prime लिखना, right? So let me rewrite this term so it will be clear. So I am writing now that is partial x prime. So if I put now, if I will be equal to j prime, तो अगर I किसके बराबर होगा? j prime के बराबर. तो in that case, so this term ये term बन जाएगी, क्योंकि if I write now this partial x prime j by I, right? So if I equal to j prime, so this becomes partial x prime j by, so that's equal to 1. Okay, so ये term 1 बन जाएगी, and what is this? So this will be f j prime, right? Because I equal to j prime, and similarly our right hand side will be equal to m, and this term again will be equal to 1, and this will be a j prime. So what does this indicate? So that means we are moving, where we move our this frame from some, so we are moving from that f I to f j prime, right? But the form of the equation will be the same, because in both the cases we have that, in one frame we have that, in one of the frame we have that f I equal to mai, and in some new frame, so that's m aj prime. Okay, so that means we are moving from some fi to fj prime, right? But the form of the equation this, it remains, it is covariant, right? Although the components can be different, because the the components will change if you transform, if you make some translation, or you make some rotation of this coordinate axis, right? So, but the total overall the form remains covariant, right? Now, in addition to that, so this was all about this. We have discussed, let me revise, we have discussed this vector transformation, we have discussed it. So, so we have different kinds of transformation, like between two inertial frames, we have discussed this Newtonian, this relativity, special relativity, what are the basic postulates there, and what kind of equations are involved in different kinds of these theories. And one important point that repeating this time, so that any theory of relativity is based on the foundation of what remains invariant. So like, so every theory, any theory of relativity is based on the foundation of these scalars. So that means because scalars, they remain the same in all the frames of reference, right? And then I also talked about that we have different kinds of also other transformation, like that conformal mapping, and we can have this space inversion or time reversal, or we can have rescaling also, right? So these are some other transformations that maybe you may uh, encounter in some coming lectures. And now the next topic is, if you talk about now the vectors in quantum mechanics. So we have these vectors in quantum mechanics. If we have some vector in some three-dimensional space, right? So